So, if there was an important component of geometry, like we've just talked about, like lines and segments and rays, I would say that this lesson encapsulates probably the second most important foundational concepts of geometry. Now, some of these you may know. Some of these you may know not at the depth that I need you to know them. Some of these may not be familiar, but you must know these and know them so well, like the back of your hand, that you can just say them and define them and do them in your sleep. Because these are going to be pieces of language that we use on a regular basis, and you've got to know them. You cannot speak my language without these words and these understandings, okay? So really, really important lesson today for us, and quite a bit of learning to do before we get to the practice. So I say that on the front load to say, we're gonna have a pretty long chalk talk, and then I'm gonna expect you to be able to go out and do it, okay? So pay attention. Don't zone out during the chalk talk, because I'm gonna expect you to take all of these things and apply them as we get a little bit further along in the lesson. Everybody get what I'm going with that analogy? Okay. All right, cool. So then, let's talk about this concept of an angle. What is an angle? All right, so an angle is formed by two rays, and really, an angle could be formed by two lines or two segments. And actually, that's not the only way it can be formed, but we'll start with that, okay? So when I say rays, I'm really talking about rays, lines, segments, any kind of straight path can form an angle. And what an angle is, I want you to circle that word, swoop a little arrow up here. The angle is actually the space between the rays, the lines, or the segment. Okay, so over here, you can see I have this diagram drawn. This space in between those two rays, that's what we call the angle. It's the space in between, okay? And each of these things over here have a very particular definition and name and way that we talk about them, and it's important that you know all of the parts and the pieces of this. So when I refer to the angle, I'm referring to the space in between here, okay? Now, these two rays, lines, or segments have a common endpoint. Okay, you can see here that this ray, ray BA, and ray BC have a common endpoint of B. And that's what we call the vertex of the angle. So the vertex is the common endpoint, or the place where the rays, lines, or segments meet. Okay, that's what we call the vertex of the angle. So if I'm talking about this space right here, this angle, then if I say what's the vertex of that angle, it's the common endpoint of the two straight paths that formed that space in between. Make sense? That's the vertex. Okay?
So would you say point B is the?
You would say point B is the vertex. If you were to write it, you would just write it with the capital letter B. Yep, exactly. Good. Excellent. And I mean, like when we're talking about, if I say, hey, John, what's the vertex of that? You can just say B. That's fine. Yeah, that's good enough for me. Now, the rays themselves, and again, the rays, lines, or segments themselves are called the sides, and we'll put in parentheses here just to kind of fill out that wording of the angle. Okay, that's a big one right there. I just used a notation. I've used it once, I think once or twice before, but you're going to see me use this a lot. This is our notation for angle. In fact, let's just, so that we're clear, write it down up here. This symbol means the space in between two straight paths. Now, when you write this, it's very important that you come down on this slope line and then flat across the bottom. And you'll notice that this bottom sits like at the bottom where I would write my sentence or my words, right? What is important that you don't do is that you don't go like this. That's an inequality sign. That's a less than sign. And there's a difference between angle and less than. You want to get it down and then flat across the bottom. That's how you properly write the angle symbol. Okay, everybody good? Properly write the angle symbol. Okay, so the rays are called the sides of the angle. So if I asked you to name the sides of the angle, what I want you to do right now is I want you to write the name for one of the sides, and then we'll do a little ampersand, that's my little and sign. So you're going to write the name of one of the sides and the name of one of the other sides of this angle over here. Okay, go ahead. You write those names in proper geometric notation. Give it a try. This is your opportunity to try. Don't wait for me to write it down. You try. It's all right if you get it wrong. Erase it and fix it, but try. You should have put that. How'd you do? Okay, so we talked about the fact that these are rays. We haven't done a whole lot of notation with rays yet. And look, you can see the common endpoint or the vertex written right in the two names, okay, of the sides. So you can put all of that together. Matthew, question. We'll talk about that. That's a good question, okay? So the angle itself, though, and this is where I want to be very clear about. The angle itself is the space in between. That's what I want to be clear on your language of what you understand an angle is. It's a notation of space in between two rays or lines or segments, okay? Now, the way that we name an angle is that we use 3 letters, and those letters refer to points, namely the vertex and 2 points on the rays, okay? And the middle letter, we're going to double underline this right here, must always represent the vertex. So here's how we name an angle, okay? We're going to use 3 letters. So you can see we have 3 points here. We have points A, B, and C. The middle letter in our list of 3 must represent the vertex. So rays, you can name, think of directional. I'm going to start at point A, move to the vertex, and out to point C. Then I would name that angle A, B, C, like that. That's how I would write the name of that angle. But angles can be named in multiple directions. And so I could say, well, I'll start at point C here, go to the vertex, and then out through point A. So I could also call this angle CBA. Both of those are acceptable. But notice what's important about both of those. The letter B is in the middle of the name. Do you see it? The naming actually visually represents the angle. It's a point to the vertex and out to the other point. The outside points are on the outside of the name, the vertex is in the middle. The outside points are on the outside and the vertex is in the middle. This is just one of those things that I see just miswritten all the time in geometry. And this is one of those things that just knocks points down on assessments, right? You must learn to communicate clearly in writing. Just like you use the proper notation for ray, line, or segment, you must name your angles correctly. Okay, now, there is another way to name angles, okay? You'll see it. You need to know about it. But I'm going to tell you right now, if you always want to get your angle name right, just use 3 letters. You can always name an angle with 3 letters and it'll always be the right format. There are certain situations where we can use a single letter to name an angle, but that's only if there's one angle located at the vertex. Notice that our vertex here is B, right? And we only have one space in between indicated in our drawing. We could call this angle B. That's a possibility as well. For now, that's a possibility. However, let's just say that we had this. And I'm going to have you draw a little line out this way. And let's put an arrowhead on that. And then I'm going to have you draw another line kind of just going out this way. Like that. And then let's put a point out here and let's call that D. Okay, you got that added onto your drawing now? Now watch this. This right here is angle ABC or angle CBA. It is no longer okay to call that angle B. Why? Because there's more than one angle that shares the vertex point B. Because if you say to me, hey, Mr. Farkas, that's angle B, I don't know if you mean this angle B, this angle B, that angle B, or watch this one, that angle B. There's a lot of angle B's there. So you've got to be specific about your naming of your angles, okay? And which is why I say this is okay. know it, see it. But if I were you and I wanted to make sure that I was always naming my angles correctly, I would always just use 3 letters, making sure my vertex is in the middle. That's always going to help you be more successful. Because if I wanted you to name this, I want you to tell your neighbor right now what the name of that angle is, because I'm going to ask one of you. You got 5 seconds. 4, 3. Okay, coming to you. All right, Giada, what is the name of this angle right here? Good, sure. DBA or ABD. Perfect. That's what you should have told your neighbor. Okay? All right, one more time. Let's test it out. Okay? What is the name of that angle right there? Tell your neighbor. You got 5 seconds. Okay. Noel. DBC would work for that one. What else would work for that one? CBD would work for that one as well, right? Okay, so again, knowing how to name your angles, okay, knowing how to name your angles is going to be important for you. All right, good. Everybody okay so far? Right? Specific. Angle is the space in between our straight paths, right? When we talk about an angle, we have sides to that angle. Those are either raised lines or segments. We name those using our ray line or segment notation like we talked about here. And when we name our angles, we use 3 letters to name our angles, always making sure that our vertex is the middle letter. So then let's talk about this thing in here, okay? When we are referring to the measure, now we're talking about like distance or length on our line segments, but now we're talking about the measure of an angle, okay? We write that naming like this. You notice that little M that's out in front there? Notice that that's an equal sign. This is number language. You can see the equal sign. And when we put this little M in front of that angle sign, we are saying the measure of. Just like when we wrote our line segments without any marker above there, that was referring to the measure of segment BA, or well, yeah, it would be the segment, right? We can't measure razor lines, right? And so this would be an example of figure language for angles. This would be an example of number language for angles, okay? Now, this little symbol, circle this little symbol here, right? And swoop an arrow over here. This is read 60 what? What? Degrees. Okay, so let's talk about degrees. Super important. A degree, let's jot this down right here. A degree is a unit of measure around a circle. So a degree is a unit of measure around a circle. Wait, say what? I thought you just said that this was the space in between 2 straight paths, Mr. Vargas. What are you doing with circles? Well, let's do this. Let's draw here. Do your best to draw. We'll draw maybe like half a circle. Let's draw half a circle. I could draw the other half a circle here. Next week, this is where this becomes very, very important. Because what does this create for us?
Perfect circle.
Perfect circles, right? Okay. It creates curved lines that are equidistant from another point in space. That's the definition of a circle, right? And it creates for us the ability to measure angles, because angles are measured in terms of degrees, and degrees are units of measure around a circle. So really, what we're talking about when we say degrees is tick, 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 like that across this little circle, okay? And so if I say that this angle here, that space in between those 2 line segments is 60 degrees, I'm saying it's 60 ticks around a circle. Important, important, important language that you need to know. All right. So then let's talk about types of angles. And this is oftentimes referred to as classifying angles. So we're just going to write the word classify here. So if I tell you to classify something, okay, if you've taken biology and you do classifications, you're organizing things into groups. That's what you're doing. That's what classifying is. You're organizing things into groups. All right, so right here is some key vocabulary for you. We're going to write key vocab, and we're going to swoop an arrow over here because this is super, super important, okay? So right here you can see I've got 2 rays and a space in between, okay? Again, 2 rays and a space in between, 2 rays and a space in between, 2 rays, yeah, and a space in between. This is like when I took my yardstick and I just opened it all the way around the other way, okay? So what we're talking about here, everything in this classification hinges around this one right here. So this is what we call a right or square, either one of those names, a right or square angle, and that is exactly 90 degrees. Oh, yeah, sorry. Right. Right or square. Thank you. Right or square is exactly 90 degrees. Okay? These two then are related to this one. This one is less than 90 degrees. You can see that, right? So again, if I'm taking my yardstick, right, and I'm going tick, 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 and I'm opening it up this way, here I've stopped short of 90 degrees, whereas here I've gone past or greater than 90 degrees. Can anybody raise a hand? Please don't shout it out. Raise a hand. Can you tell me what the name is of the classification of angles when we go less than 90 degrees? Liam? Okay, that is an acute angle. Okay, anybody know the name for greater than? Josh? That is an obtuse angle. All right, and then this one, again, with my yardstick example, right? I took my yardstick and I opened it all the way up until one yardstick was pointing in one direction. That's one of the rays of the angle. And this one is the other ray of the angle. And this one is exactly 180 degrees, like we just talked about. Anybody know the name of this one? This one's one of the more confusing ones for students because they look at it and they go, well, but Mr. Farkas, that looks like a line. Good observation. This is called a straight angle. That's kind of a logical name for it, right? You take the angle and you open it up to the extent that it creates a straight path going in both directions. Classifying angles: acute, obtuse, right, and straight. Super, super important language we will use all semester. Everybody good so far? Yeah? All right. So then, how about you do a little application here? All right? I want you to do these 4 questions right here. I'll give you 2 minutes, and then I'm going to ask you to give me those answers. I'm going to call on you, so make sure you share your answers with your neighbor, check in, and see what you do. You are naming the vertex of the angle in example 1. You're naming the sides of the angle. You're giving 3 ways to name the angle, and you are classifying that angle. Ready, go. Coming to you guys for the vertex of the angle. Alexa, what do you got? Vertex of the angle. Nope, the vertex of the angle is always going to be the common point where the sides of the angle meet. So if the angle is this space in between, what common point do the sides meet? Point K, right? That would be the common point that they meet. So the vertex of this angle would be K. All right, good. All right, naming the sides of the angle. Gavin, what you got?
The sides.
We've got that beginning point at K, that's that shared common point, right? And then we have the ray notations at the top. All right, giving 3 ways to name an angle. LKJ, sure, angle LKJ. That works, right? Because that's starting at point L, moving through the vertex of K and out through J. Angle LKJ. That works good. All right, another name, Ruby. Angle JKL also works very good, right? And that, again, is just starting at the other point that's on the other side and moving through the vertex. Important about both of those is that letter K. All right, last way to name this angle, Peyton. Yeah, this one is okay because we don't have any other angles coming off of here, right? And so in that case, it's okay for us to use angle K because that's clearly the space in between that we're talking about there. Okay, classifying the angle. Noah, what do you got? Yeah, this is obtuse, right? This is greater than 90 degrees, but less than 180. That makes this an obtuse angle. Good? Okay, all right. Let's try some more. Naming the vertex, the angle, naming the sides, 3 ways, and classifying. All right, now let's see how you got this down. You guys do all these. I'm just going to pop the answers up for you here at the end for you to take a look and see how you did. You're going to go ahead and do example 2. Go ahead, give it a shot. Come up with these right here. Take a look and see how you did. Right? And now, something to talk about that's really important here. How do you know that this is a right angle? It's got that little square marker right there. Okay? This is going to happen. I'm telling you right now, it's going to happen. Do not assume 90-degree angles. If you are not told in your diagram with a certain type of notation or in the wording, you cannot assume that an angle is 90 degrees even if it looks like it. Do not assume that. Because listen, 89.999999999999992 looks a heck of a lot like 90 degrees. And it is not. Okay? So please do not assume 90-degree angles unless you are given it in the diagram or told somewhere in your problem or given some certain notation we'll talk about a little bit later in the lesson. But you cannot assume that you have 90-degree angles unless you're told that, okay? All right, let's talk about then congruent angles. This is another piece of key vocabulary for us. Let's just write this down so that we don't lose sight of this. Okay, another piece of key vocab to keep track of. All right, so just like we had congruent line segments, we can have congruent angles. And so we can say, if the measure of angle A, and we're going to use the example over to the side here, is equal to, notice I didn't say the congruent sign, the measure of angle B, that's because I'm using number language and not figure language. If the measures of the angles, the degree measures, are equal to each other, the numbers are equal to each other, then the angles are congruent, and that would be written as angle A is congruent to angle B. Just so that we're clear, this is number language, while this is figure language. Refers to the same thing, but again, as I mentioned when we kind of introduced this idea with line segments, that we can't do math with figures, but we can do math with numbers. And depending on how sticky your geometry lessons are, you might have to change between figure and number language to do math or use certain propositions, theorems, postulates, those types of things. So we'll talk about some of that. Now, the other thing I wanted to talk about was, how do you know from a diagram if two angles are congruent? Well, this is one way that you could tell. You're given two angles and you're given equal degree measures, right? I could say, based on that diagram right there, that measure A is equal to measure B, therefore angle A is congruent to angle B, okay? There's another way that you might see, and so we're going to kind of draw a couple of little more diagrams right here. Another different way that you might see, let's draw another angle A here, and another angle B here. And you might see something like this. Matching arc marks. Just like on segments, we have those little matching hash marks that tell us the line segments are congruent. In angles, we can have matching arc marks, and that will also tell us that the angles are congruent. Another way that you might see this, and this is kind of more of an old school way, but it could pop up. Let's do another angle A here. And another angle B here. You might see an arc with a slash through it. And if you see that, that would also indicate that your angles have the same degree measure and therefore are congruent. I'll show you one other way on another problem that we're going to look at in just a minute, okay? But there are multiple ways to notate this. You need to be familiar with all of them because they may pop up at any given point in time. Let's keep rolling. Backside. Super, super important information in today's lesson. Another piece of key vocabulary for us that you need to know well is an angle bisector. Okay, an angle bisector. So let's talk about what an angle bisector is. An angle bisector is a ray, again, or a line or a segment. An angle bisector is a straight path that divides an angle into two congruent angles. So in the diagram to the right here, ray BD is an angle bisector. Therefore, angle ABD is congruent to angle DBC. Or likewise, we could say the measure of angle ABD is equal to the measure of angle DBC. Did you catch that? You are told in the problem that ray BD is an angle bisector. Well, okay, an angle bisector would have to cut an angle in half. So what is it cutting in half? Well, it's obviously in between angle ABC. It's in angle ABC, so then it must be bisecting angle ABC, which would mean that from A through B to D is going to be congruent from D through B to C. Now notice something on this congruency mark. You see how it's one consistent arc all the way through? That's another indication that ABD is congruent to DBC. Let's just draw another little diagram up here. What if we had, again, like this, we're just going to do another A, B, C, but this time D was down here. Does that look like an angle bisector? It doesn't look like it, but we can't rely on the drawing. But if I were to mark this with one single arc to indicate that, right, or the way that I would indicate that is I would put one arc here, and then I would put two arcs here to tell you that those two angles are not congruent. Just like on a line segment, I would put one hash mark and two hash marks to tell you that those line segments are not congruent. That's yet another way of indicating that. So if you see one consistent arc through those two angles, you could think of that like the notation that I showed you above that has a mark here and a mark here, and that means that those angles are congruent, and therefore this is an angle bisector. You got to be able to go both directions on that street. When we start our lesson next week and we talk about biconditional statements, and I've mentioned this previously, this is a sidewalk you can walk both directions on. Okay, listen to what I say, okay? If ray BD is an angle bisector, then angle ABD is congruent to angle DBC. Now I'm going to go the other direction on the sidewalk. If angle ABD is congruent to angle DBC, then ray BD is an angle bisector. Did you see what I did there? It's the same thing, the same relationship, but I walked the other direction on the same sidewalk, and you've got to be able to do that as well. You've got to be able to use that reasoning so that if I give you this picture and I don't tell you that ray BD is an angle bisector, you need to be able to discern from the picture and the congruency marks Wow, okay, angle BD, or ray BD, is a angle bisector of angle ABC. You have to be able to discern that and say that. Did you catch what I did there? Give me a rating real quick. 5, totally got it. 1, completely lost in what I just talked about. Let me see around the room. Okay? Okay, got to be able to bounce back and forth, right? If I know this, then I know this, or the other way around. If I know this, then I know this, in these two ideas being related to each other. Okay? All right, let's talk about perpendicular lines, another key piece of vocabulary for us. So perpendicular lines, this is a word that you must know. Perpendicular lines are two lines that intersect. That means they cross each other, right? At a right angle. How many degrees is a right angle? 90 degrees, right? Okay. We have a symbol for perpendicular. You need to know this. This is the symbol for perpendicular. When we write that, that can be as easily replaced with the word perpendicular as anything else. By the way, we have another P word that we use all the time. Let's just jot it over here. Parallel. And we have a symbol for parallel. And it looks like that. Right now we're talking about perpendicular, but seems like an appropriate time because parallel and perpendicular are two key relationships that we're going to deal with when we talk about segments, lines, and rays.
So how are you getting that out?
No, because if we're talking about lines being parallel, we'd be using figure language, right? So it would be something like segment AB is parallel to segment DE. We wouldn't say 11 is parallel to something else. So it's a good question. But yeah, so that kind of emphasizes the difference of the idea of figure language, right? Because we use these notations when we're referring to figures, okay? All right, good. Yeah. Okay, so in the diagram to the right, all right, here we can see that line L is perpendicular to line M. It's kind of a lame lowercase m, but you know. So line L is perpendicular to line M. And again, we don't assume this. We know this because we're told that with the little marker there. Okay, perpendicular lines. This concept is so critical to so much of what we're going to see in terms of relationships. And this is this idea of a perpendicular bisector. Key vocab. Now just take these two words that we've been working with and put them together. A perpendicular bisector is a line, a segment, or a ray that is perpendicular to another line, segment, or ray. Well, it would have to be actually to a segment because it's perpendicular. Watch this. Oh, there it is again. Moving the card to the top of the deck and the bottom of the deck. If you have a perpendicular bisector, you have a 90-degree angle, which is important to work with, and you now know the midpoint of a line segment. Again, critical concepts. Super, super important concepts. Okay? So in the diagram to the right, line LM, see, because it extends in both directions, is the perpendicular bisector to segment PQ. Got to write that correctly. How do we know it's the perpendicular bisector? Okay, so it makes a 90-degree angle. That's the perpendicular part. How do we know it's a bisector, though? Because we have these congruent marks on each of the line segments. See that? From P to here, this middle point, which will usually be labeled with a letter, and then from here to Q are the same distance in length because of those hash marks, which means that this is the midpoint of PQ. Perpendicular bisector. You're going to use this to make a perpendicular bisector. Wait, I thought you said that thing was for circles. Oh, it's for so many things. So many relationships. Wait do you see how powerful this tool is. You're going to have some fun with that, trust me. Okay, let's have you do some work here. Now we get into a really good diagram. Look at that picture. That is fantastic. There's all kinds of good stuff in there. All kinds of congruency marks and rays and angles and lines and there's just tons of stuff in there. So why don't you write another name for angle CBF, name the sides of angle EBD, classify angle ABC, give an example of an obtuse angle, name two congruent angles, and a perpendicular bisector. Feel free to work with your neighbor on this one. All right, go for it. There are some answers. You might have something that's a little different, but let's take a look and see what you came up with. Another name for angle CBF. Okay, this is the only possible option, would be angle FBC. Can't call it angle B because we've got multiple angles coming off of B. So it could be CBF or it could be FBC. All right, name the sides of angle EBD. All right, well, I got to find angle EBD. Where is that? All right, well, that's this space in here, right? Okay, so if I wanted to name the sides of that angle, then I need ray BD or ray BE. You could have said segment BE and segment BD too. That would totally be legit. Nothing wrong with that. What you can't say is ray or segment BD and line EF. That would not work because the line extends past the vertex of the angle and creates multiple angles that, does not give us a specific name for that space in between here. Okay? Classify angle ABC. Angle ABC. So like that. That's a straight angle. 180 degrees. Opened all the way up. All right, name two congruent angles. I went with angle EBA and I went with angle CBF, and I went with those because I have congruent arc markings there. Anybody else get anything different, by the way? No? Ethan, what did you put? For D. No, for E. That's what you put? Anybody else put anything different for E? Did I skip D? An obtuse angle? Okay, yeah, obtuse angle. I put EBD. Anybody got a different one for EBD? There's other obtuse angles in here. What'd you get, Payne?
EBC.
EBC. Yeah, that would be an obtuse angle. Yeah, that would be on this side over here. That would be an obtuse angle. Sure, that would work. Okay, all right. John?
Really quick, could you mathematically read your answer? I got the same thing, but I'm
For this one or the next one?
the next
For E?
Yeah,
So I got angle EBA is congruent to angle CBF.
and then the little squiggly line above the
Congruent.
congruent.
That's our congruent sign. That's our figure language for saying the figures or the actual spaces in between are the same. We could say the numbers, the measures of angle EBA and CBF are equal to each other, but we don't know what those numbers are. So in this case, we have to use our figure language. There are other congruent angles, like, for example, how about this one? Angle ABD and angle DBC. What do you think about that? What's the measure of angle DBC? What's the measure of angle DBC? 90 degrees, right? What's the measure of angle ABC? What's the measure of it? 180. If this is 90 and this makes up the other part of the 180, what does this have to be right here? It's got to be 90. Oh, that's a big, big thing to know right there. That's a big, big thing to know right there, okay? And that's actually going to lead us into what we need to talk about next. So this is a must-do homework for you right here. Okay, that's a must-do homework for you right here. Example 4.
Moving on.
So time, we've added some key vocabulary, right? It's about time we add a new tool to our tool belt. Here we go, new tool to the tool belts. This is the angle addition postulate. That sounds really familiar, Ms. Varg. You sure we haven't talked about that tool already? Well, we've talked about the segment addition postulate. Now we're going to talk about the angle addition postulate. Now take a look over here. If point D, watch this, this is really important language, is in the interior, the inside of angle ABC, that's going to create two angles. Now, not necessarily bisected, right? We don't have any indication here that these angles are congruent. We haven't been told that. And there's nothing in the wording that tells us they're congruent. But we do have this point D that we've drawn ray BD through, which is now split up angle ABC into two parts. See that? We originally started with angle ABC, and now it's been split up into two parts. And so what we could say is this, watch. The measure of angle ABD, find the space, go ahead. See it? You see where the measure of angle ABD is? Plus the measure of angle DBC. When we add those two numbers together, well, we should get the measure of angle ABC. If we take the measure of angle ABD, this space in here, and then we combine it with the measure of angle DBC, this space in here, what that's going to total up to is the measure of angle ABC, that space in there. You might think of this like part plus part equals what? Whole. But this is just, let's make a note over here now, for angles. So we have part plus part equals whole for segments, and now we have part plus part equals whole for angles. Two angle addition postulates, a segment angle addition postulate and an angle addition postulate. We have two addition postulates. Two, part plus part equals whole. All right, let's see how this works then. If I told you the measure of angle ABD was 48 degrees and the measure of angle DBC was 78 degrees, find the measure of angle ABC. Let's start with an algebra problem. Write me an algebra problem that you could solve for the measure of angle ABC, and we'll use X to represent the measure of angle ABC. Go ahead, try it. Set up an algebra problem. Problem should have looked like that. Because we're looking for the whole. The whole is what we don't know. And then we would just combine our like terms, and we would end up with an answer that looks like this. X is equal to, what's 48 plus 78? Watch this. Watch me. Watch me. 126 degrees. Oh my goodness. Don't forget the unit. How many of you, no matter how many times I said that on the last test, got your units wrong, your squares and your cubes, or left them off altogether? Do not forget your unit. Pretty please. It pains me to mark you down, but I will do it every time. Don't forget your units. That little circle is so important when we talk about degrees. Okay, cool. Let's go the other way. Write me an algebra problem. If you know the measure of angle DBC is 74 degrees and the measure of ABC is 119 degrees, write me an algebra problem and then figure out the measure of angle ABD. Again, remember, this is all about starting with the algebra problem. Like that. Starting with an algebra problem and ending with an x equals. Don't forget your degree marker, right? 45 degrees. Here we go. Number 3. If the measure of angle PQR is 141 degrees, you need to find x equals over here. You need to find x equals, and then you need to find the measures of these two angles. If you need to end up with an x equals so that you can plug it back in here and plug it back in here, right? Then that means you need to start with a something equals something. So you have to start with an algebra problem here in order to get to an x equals. Go ahead, see what you can do. Okay?
I'm confused on how you set up number 2.
If you're moving in the right direction. If you're moving in the right direction, you should have started with that algebra problem right there. Right? It's part plus part equals whole for angles, and we know the measure of the whole, PQR, so that's going to go out here, so we've got part plus part equals whole. And then from here, you solve. Go ahead and solve that down to x equals. Going down to x, you should have come up with that. How many people got there? Let me see. Okay, that's pretty good. That's pretty good. It's pretty good. Okay. If you're struggling with this right here, that means you still need to go back and review solving equations. That's the, and then you do the math part of the problem. This is the, what geometric principle am I using to set up the problem? This is angle addition postulate, or part plus part is equals whole for angles. And then I do the math. And then I do substitution to take my x equals 6 and go back and figure out my actual individual degree measures here. So if I wanted to know the measure of angle PQS, that would be equal to 13 times 6 plus 4. And then I would add that across, get my 78 plus 4, and I would get 82 degrees for the measure of angle PQS. And if I wanted to know the measure of angle SQR, that would be equal to 10 times my same x minus 1. So then that's 60 minus 1 is my 59 degrees right there. And if the math problem is written correctly, which they usually are, part plus part, add that up in your calculator right there. Go ahead. 82 plus 59. What's 82 plus 59? It should be 141, right? Because part plus part equals whole, right? Yeah. See that? Should be. That should be right. That's a good check for you when you're doing your problems. Same thing going with the bisecting stuff, right? So watch out for angle bisectors.